your schedule so that it says project number 2 is due a week from today. So that will be March 12th. Okay, is the deadline, due date. Now remember, I do not take late projects. Now, the last page of this project, you'll see a bunch of sites that you can go to try to find data. If you have trouble finding data, okay, you'll have a better sense of what I mean by that after today's class. I got that from the librarian. There's 2 librarians that know about this project, and they'd be very happy to help you. One of the librarians' name is Eliza Harrington, and the other person is Eric Poulin. So those are the 2 librarians. If you have any trouble finding any data that you're interested in using for the project, they'll be very glad to help you. Also, I've gone through all those sites with the librarian, so if you want to stop by my office, I'll help you with that as well. And I've asked Liza to make a video for this class, but she can't do it till next Tuesday, the earliest. So that's not going to help you, because by then you should be pretty much done with this. So do not, this is the kind of project where you do not want to procrastinate. Okay, do not procrastinate. That's my last famous words. Okay, it takes a little time, but not a lot. The most of the time is really investigating what kind of data you're interested in looking at. So I often encourage students to think about what you're interested in. One of my students, just for an example, let's see if I have it in my little Dropbox here. Let's see what class it was, and then I'll get going. Open up. Okay, one of my students was a veteran, and I think it's in day 14. Will this show files or just Word files and notebook files? Do I have to put anything in here to see everything? So I thought it was in day 14. I'll find the file. He was a veteran, so he looked at the 2 variables that he looked at were the number of troops in Iraq over time, and so that's what he plotted, and he found the line of best fit for that. So depending on like where your interests are, whether they're your academic interests or a hobby that you have, there's probably data out there. If you're interested in the environment, again, those sites that I gave you, you can find lots of statistics there. Or you could gather your own. Like one student measured, I mentioned that there's a relationship between the length from your elbow to your wrist and your foot size. And I'm not flexible enough anymore to get my foot up there, but there's a relationship. So someone went around measuring people's lengths from the elbows to the wrists and their foot size. He got like 20 different measurements and then plotted those. So that's a little bit, we're going too far into today. You may not know what I'm talking about yet. So let's take a look at what we're going to do today. So you want to read this for us, Paul?
That one variable can be estimated. So that one of the variables can be used to predict or estimate another is called regression. This class will look at the simplest form of regression.
Okay, so again, we're learning all of this mathematics so that we could perhaps someday either do some research or look at a journal article, whatever field you're in, and understand what models are. So we gather data. We hope to use the data for some value. That may be to predict an outcome, or it may be to estimate an outcome. If you're within your data range, you're estimating an outcome. If you're outside of your data range, you're predicting, right? The future or the past, right? So in order to do this, we have to come up with a mathematical method so that when we gather the data for two quantitative variables. But now quantitative means we're not out looking at gender or hair color or eye color, things that are categories. These are numbers, things that we can measurement on a real number line. They have, we can actually measure their values. And this process is called regression. Now, by the time we're done in this class, we're going to do more regression than linear. But we're going to start with straight line or linear regression because we've just spent a section on straight lines and interpreting slope. So let's take a look. And I've actually used some of the data from our book here because I thought this was an interesting data to look at. So someone want to read us what this data is all about? Tony?
Table 1 below gives the nationwide infant mortality rate period from 1950 to 2000. The rate is the number of infants who die before reaching their first birthday every 1,000 minutes. Does there appear to be a relation? The rate of U.S. infant mortality here.
Okay, so here's a table. It goes from 1950 to 2000. And then this says that 29.2 out of 1,000 infants died before their first birthday. And then it shows you the data for each decade after that. So the first question is, does there appear to be a relationship? That's what we're trying to measure at some point. But is there a relationship, do you think, between the year and the rate? Yes, no? Yes, okay. And how would you describe that? You don't have to be fancy mathematical. What might you say? Real in simple everyday language about the infant mortality rate between the, right, so as each decade goes up here, right, from 1950 to 2000, the infant mortality rate decreases, right? So you can say that any way you want in your own words, okay? So you notice, I'm gonna shorthand it, but you write it out in a sentence. So as the year, which is really decades here, as each decade increases, what happens? The infant mortality rate decreases. That's how I'm going to write it. Okay. So that's one of my variables increases, the other one decreases. So, these tables are fine. You can kind of get the overall idea about what's going on with the data like we just did. But it's really, really nice to see this in a graph. So we will often, most of the time, every time, at least in this class, we will take our data, and in order to have a clearer view of what's happening between the two quantitative variables, we will graph them. So what we have along this axis is each decade. So this represents, again, okay, my plots didn't come through all the way. So I have a 0 right here. What do you think that 0 represents from our table? 1950, right? Because the next point is what? 10, right? And then we have 20, 30, 40. So our independent variable, let's call it X for now, is the number of years since 1950. And we often start this because we like starting at 0 rather than having to go all the way out here, right, to 1,950. We just kind of bring everything in so we can start right at 0. So this first point here, if you looked at your data table, what's the actual data point right there? The actual data point, year 0 is 1950. And what's the outcome here? What's the Y value? Is it 29? Look at your data table. I want the 29.2. Okay, so that's the actual data value. What about the next one? In 26. Okay, so these are the actual values, 20. Then what's the next one? Huh? 12.6. Okay, so these are the actual values from my table. Okay, so now when we look at this, when we plot this data, when we plot the values for two quantitative variables, this is called a scatter plot because the points are kind of scattered. Okay, now sometimes they can be scattered and they won't make any picture at all. Right? They won't have any form to them. They could be like a big circle. Anybody play Candy Crush, you know that big circle gumball thing you get? Nobody plays Candy Crush? Okay. Well, let me tell you, one of my students at the end of last semester told me about Candy Crush. And I've been on the same level for a month, over a month. And I curse him every night because I can't get through this level. And I'm not even telling you what level it is because I'm so embarrassed. But anyway, so Robert, I may talk to you after class. All right. So, you know, sometimes the picture won't look like this. In fact, if I say look like this, what form does this picture have to you? What's it look like? A line, right? It looks like a line. So when I ask you a question, does there appear to be an overall pattern or trend to the data? You look and you say, yeah, there does. The trend, how might you describe the pattern or the trend here? What might you say? Ooh, you're getting really fancy on me now. Did you read ahead, Paul? Oh, you took statistics. Okay, so Paul took statistics, and he's saying there appears to be, ooh, we're going to use big words now, a negative association. Okay, well, we'll get to what that means in a minute. And that's a perfect answer if you've taken statistics. Where do you think the negative part comes from? Because the line goes down. We just saw that as one of our variables increased, as we increased in time, our infant mortality rate went down. So there's a negative association between the two, right? And the overall pattern is, would you agree there appears to be a linear relationship between these? You said you could probably form a line, right? So there appears to be some kind of linear relationship where as one of your variables increases, the other one decreases. So how strong do you think that relationship is? Now, you don't really know how to measure this yet, but does it look like it's a pretty good straight line? So fairly strong, pretty strong, not strong at all, very strong? What do you think? Fairly strong. That's kind of a good way to get out of fairly strong. You're not saying, yeah, very strong. Anybody want to say very strong? Very strong. We got some very strongs out there. Okay. All right. Okay, so what I want you to do right now is I want you can use your studio bookmark or any straight edge you have to draw a line that you think visually best fits the data. That means your line comes as close as possible or exactly on all of the actual data points. You're not going to be able to hit them all because they don't fall in a perfect straight line, and that's not our goal. But you draw your own straight line through that data the way that you think it fits the data the best. And I'm going to do my line, and then we'll see how close we get to the actual line. All right, so you just draw a line through, eyeball it. It's called the eyeball method. Is everybody drawing a line? No? All right, now you're done. Okay. So the disadvantage of having you all draw your own line is that it's not unique. And I would have as many different lines from models out there. The equation for your line would be a model, but I'd have, right now I probably have 20 people in here. I'd have 20 different models to work from. So the good news is there's a mathematical method that we use to find the line that fits the data best. It's called the line of best fit or the regression line. Okay, the line of best fit or the regression line. Now this is getting a little bit into statistics, and I can't help it because I have a degree in statistics, so I always got to go a little bit more in algebra than. So this is, when I plot this is the line of best fit that the computer comes up with. There's a real fancy name for the line of best fit. It's called the least squares regression line. And let me just tell you why, real briefly, they call it the least squares. Because if you take a point, the actual data point here, this was 1960, right? With 26 was the infant mortality rate. If you dropped a vertical line to that regression line, that distance is what we call the error. Because the error says, I didn't hit that one right on the nose. My estimate, if I use this line to estimate this point, I'm going to be a little bit below the real infant mortality rate. So what they do is every time there's an error, they make a square where all the sides are the same length as that error. So you can calculate the area of that square. Okay. Now notice this one has no box around it, no square. Why do you think? It went right through that point, no error. Now this one has the biggest square, doesn't it, of all the points on the line. So if you add up the sum of all these squares, which are formed by making a square from the error, this line has the smallest sum of the squares. It's the smallest amount of error. And all you have to do is put any other line through there. Let me just kind of be a little ridiculous, like I'll do that. Like suppose I did that. Now you could tell if I dropped a line from each of these points, look at how big my square would be. Look at this, down to this line. I mean, this would be huge. You can see already the sums of those squares would be much bigger than the sums of these squares. So the line that we fit, the line that your calculator GeoGebra is going to fit for you, does all of this thinking for you. It calculates all of the sums of these little squares and makes that sum of squares least, smallest, the smallest amount of error. Okay, and that's where this term, least squares regression line, comes from. Okay, now you'll never have to do that. You'll never see it in your book. I threw it in to show you where this fancy term came from and the idea behind the line of best fit. Okay, so when we describe an overall pattern of a scatter plot, we use these three terms. What form does a scatter plot have? Well, in our particular case, the form is a line because we're looking at linear regression. What direction does it have? Well, Paul helped us with that. He said it has a negative association, right? Negative because if I asked you what the slope of that line was on your picture, you would have said a negative slope. So you're either going to have a negative association or a positive association. So here you only have two different answers, negative or positive direction. Now the strength of the relationship, we have another statistic that measures that, and it's called little r, the correlation coefficient. And again, as any good progress shows us, you can't appreciate the amount of work you don't have to do anymore. When I took statistics back in the dark ages, everything you're seeing today that's being done by your calculator, from finding the least squares line to finding the value of this little thing that tells us how strong that relationship is, I had to grind out by hand with very large data sets. So don't say that you have a lot of work to do, because it's a lot less than, with technology. This is where the technology helps us. Okay, so we define the direction of a relationship, looking at whether or not the variables have a positive or negative association, and this is what Paul mentioned earlier. We say two variables are positively associated when larger values of one variable tend to occur. They won't always. You might get a point, you could get a point down here that's up here. Something happened in, say, medical research or something, or in people taking, or there was some epidemic. So they tend to occur. It's not always if one thing happens the other. They tend to occur together. And they're negatively associated when larger values of a variable tend to occur with smaller values. So are these, we already know the answer to this because Paul gave it to us. So we know that these are negatively associated, okay, because as our decades go up, as year increases, the infant mortality rate tends, and in this case, tends to decrease, okay? So we can't rely on our eyes to measure the relationship, how strong it is. We've got to come up with a variable, some way, a constant that will measure it. So let's take a look. As I mentioned, the way we measure this strength is with a correlation coefficient, and our correlation coefficient will always be between +1 and -1. Okay, it'll be some value in there. Okay, so let's take a look. What do you think a scatter plot would look like if the correlation coefficient was 1. That meant 100% positively associated. Which of those pictures do you think would have 1? Top one. It means it lies in a perfect straight line, no deviation. Okay? So if you had a scatter plot like that, something's wrong if you're collecting real data. You don't ever, I mean, it's really hard to find real data that lines up in a perfect straight line unless it's already set to a model somewhere. So what do you think would be the correlation coefficient for this one right here? Second picture, -1, right? Okay, so any number for R that's between 0 and 1 is going to have a positive slope. As X increases, so don't the Y. It's not going to be an exact fit. And the closer your number gets to 0, the closer it gets to 0, that means your association is getting weaker and weaker and weaker. The closer it gets to 1, it's getting stronger and stronger and stronger. And that's another whole lecture as to where's the cutoff point. And that depends a lot on what academic field you're in, social sciences versus hard sciences. Like, at what point do we say, I'm not looking at this data or trying to find a line because R is too weak? So that's another whole story. Okay, and you could have the same story on the other side with a negative association. R can be between -1 and 0. So if we went back to the data that we just looked at, when I asked you how strong you think it is, what do you think, I'm just recording your guess, what do you think the R value would be for the infant mortality rate? Some said fairly strong, some said not so strong. First of all, what sign will it have? It will be negative because it's negatively associated. So what's some guesses for it's got to be something right in here. What do you think would be the value of your correlation coefficient? -0.85. So that's strong, right? Okay, and now, Chris, you said very strong. So do you think it might be higher than that? Meaning closer to -1? Okay, what do you want to go with? 0.9? Okay, and Tony, you said fairly strong. So what do you think? -0.8? All right. All right, so those are some guesses. All right. So the formula for the least squares regression line, or the line of best fit, is found using calculus. Oh God, but we're lucky because the formula is programmed into our graphing calculators. So let's use our calculator to find the line of best fit for this data. Okay, so the first thing you're going to do is don't flip out because of all the steps, because they're all written down here for you. Okay, so you may or may not listen to me, but the first thing I would just suggest is that you watch, because they're all there. Because if you try to do it as I go through it, you'll get stuck somewhere, and I'll be 3 steps ahead of you, and then you'll be right. So the first thing you're going to do is obviously turn on your calculator, and I shouldn't say obviously, but I don't like to say obvious. Now this is one thing you'll always forget to do, and you'll keep saying, Linda, my R value is not there. So before you do anything, down here, you can do this with me. You see right above the 0, there's catalog. I want you to hit second catalog. And you should see a menu like that. And unfortunately, we can't use a letter. We have to scroll down. Scroll all the way down until you see diagnostic on. So you got to scroll down, boom, 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 till you see diagnostic on. Thank God it didn't begin with a Z. So I go right there. I put my arrow right there at diag, and I hit enter. And I hit enter again until it says done. Yeah, now I'm going to have everything I need. Okay, so that's the first thing you always do before you do any regression. You make sure your diagnostic is on. Okay, so just watch. The first thing we got to do is enter our data. We've got some data there, and you're going to have to read it to me. We're going to put them into lists in our calculator. So from my home screen, I hit stat, and again, I go to edit, and I'm going to put in this data. Now here's an interesting thing, and I always forget this myself, to clear. Okay, see how I just literally cleared off that whole column? I lost it. So I don't hit DEL clear, I hit clear, enter, and that clears my column. So I can get it back, but I just wanted to show you. If you want to get rid of values in your column, you hit clear the column and enter. All right, so I'm going to use L5, L4, L5. You can use L1, L2. So read me the data. What are my years? I'm going to start with 1950, right? We're calling that 0, the 0 year, 0. And how far up do we go? 60, up to 2000, 70, 1980 is 30, 1990, 2000. Okay. Now I go over to the next column. Would someone read me the infant mortality rates for those 6 values? 29.2, 26, 20, 12.6, 9.2, 6.9. Okay, so now I have my data entered into the columns L4 and L5. Okay, I want to tell my computer now, my calculator, to graph the data. I want to take a picture, look at the picture. I mean, we've already looked at the picture, but you're going to be looking at new data sets. So to do that, you go up here to stat plot. It's above your y equals, second stat plot. And make sure these are all off. And you're going to just go down to the first one, and you're going to turn the first stat plot on. And the first picture you get here for type of stat plot, that's a scatter plot. That's what we want. And that's where it defaults. It will always be there. And what were my data sets now? L4 and L5, right? So to put L4 in there, see where L4 is right above the number 4? So I just hit second 4. And guess where L5 is? Right above the number 5, second L5. And I like these little marks right here because I like to see them. I like that versus the little dots. And now, just like there was a standard zoom for your algebra, there's a standard zoom for your statistics. And if you go all the way down, you see your standard zoom for statistics is, I went too fast, right there, number 9. It's zoom stat. Once you press enter, your graph's going to come right out. Why don't you have a calculator? I mentioned to come up and get one at the beginning of class. And sign your name out, please. So I'm not sure why my calculators, oh, now do you see the funny picture I got there when I did Zoom 9? There's my scatter. Do you see this other picture there? That tells me something else is going on. Look, I have a y equals button right here. See how I'm trying to graph 2 things at once. So I got to clear that out. Okay, now Zoom 9, okay, is this scatter plot right here, which we looked at a few minutes ago. Okay, so there's our scatter plot. And now what I want to do is I want to actually come up with my equation for the line of best fit. Give me that equation. And this has a series of steps here. Again, they're all written down. You'll get used to it if you do this 4 or 5, 6 times, which you will be doing. So don't worry about it, okay? So I want to get my linear regression. I hit stat. I go over to calculate my linear regression line. I go down to 4. I hit that. And now I tell it where my data is located. It's located in L4, comma, L5, comma, and now I tell it I want it to put it on the line y1 equals. So to tell it to put it in the variables, I go over to vars, yvars, function, hit y1, hit enter, and there is my line. So how do I come up with the equation for my regression line? Well, let's take a look at what it says. Let's take a picture of this. Okay. All right, so here's all the data my calculator gives me. Notice their line is y equals ax plus b. That's like y equals mx plus b, right? A is just your slope here. So let's see, where are we in, okay, so here is our regression line. Y hat equals negative 0.48x plus 29.4. Notice A takes the place of your slope. So here's your value of A. I've truncated it. I've estimated it. B is like your y-intercept, that's over here. So this line is saying that in 1950, when X is 0, what's the infant mortality rate? 29.4, and what does our table say it is? 29.2. So we're just a little bit overestimating it. Pretty good. It's a pretty good model. So when I write my regression line, I take these two figures off and I put in my slope and my y-intercept. And notice I use this y hat. That y hat, now you won't see this probably in any other college algebra class. I use y hat to remind me that this line is used to predict and estimate. It's not exactly y equals. It's not the exact data. It's a prediction line. That's what we use in statistics. Okay. So there's the line, and now you can use this to estimate various things. So if I wanted to use that line to estimate infant mortality rates in 1995, the first thing I have to do is figure out how many years beyond 1950 is 1995, and that's 45 years. And my model says to take X and multiply it by negative 0.4837, blah, blah, blah. Add to that 29.4095. Your calculator is going to have all this in it, so you don't have to worry about rounding it off. Keep all the values in your calculator and then round off. So how can you do this really quickly? Remember, that line's right here in Y1 with all of the data in it, all of the values. So go to your table, right? Go to your table. And what's our value we're interested in? 45. So just put here 45. Go down and say, you can either say auto or ask, go to your table, and voila, there's your answer. In 1995, we're estimating that the infant mortality rate will be 7.6424. That's what we're estimating it will be. Okay? So you have a bunch of data sets in your activity. I want you to look at whatever data set you might have the most interest in and start getting some regression lines and data entered. Have questions? I'll be glad to help you out.